firms, including Howden and now Oak Security, where he's a senior smart contract auditor. Jose, it's amazing to have you here. We can't wait to get going. Just very quickly for everyone, if you have any questions throughout this whole workshop, just drop them in the chat, and then myself or Callum will just pick them out, and we'll let Jose know, and we'll just read them out as and when. Looking forward to an engaging session. But yeah, over to you, Jose.
Thank you very much for the introduction, Dan. Thank you to the Calyptus team for inviting me for this workshop or online event. I was indeed really happy to have the chance of talking about security in a technical sense to a wider audience. So thank you very much. And okay, so as you probably know by now, we are going to talk about reentrancy today, but not just like the common examples of reentrancy that you have probably already seen a million times and tested yourself how to exploit them or how to spot them, but to look into the wider family of reentrancy bugs, as it can take many shapes. In this case, we'll see around 5. So Dan already did the introduction, so I will just skip this. So the outline for today, first, of course, why reentrancy again? Because as I have mentioned, it is one of the most widely discussed bugs in Solidity security. So why are we keeping getting into this over and over again? So then we will refresh the basics, because although I assume all of you are familiar at least with the basic form of reentrancy, it's always okay to have a quick check on the basic stuff to clear some concepts and so on. And then we'll get into the more interesting bits that will be other forms of reentrancy. In this case, we'll see token callbacks, cross-function, cross-contract, read-only, and we will briefly mention cross-chain if time allows. So why reentrancy again? Well, the answer is quite easy indeed. It's because reentrancy again. We keep having reentrancy incidents over and over again. So although the basic idea may look simple or basic, as you can imagine, the actual job of removing a reentrancy bug at all from contracts is not easy. And this big list that keeps growing month by month is like a clear proof of that. So in reality, minimizing the number of whatever security bug in a software is hard and is part of a multi-step process. So there is no silver bullet here that can save us all from whatever bug, for example, reentrancy. But one of the first steps is to have what is called security-minded developers. So developers that not just have like deep enough knowledge to identify this common vulnerability or think about these scenarios, but that are willing to engage in security aspects. So our goal for today will be 2 goals indeed. First, to try that you learn new things about reentrancy and how it can take more forms that the ones that we commonly see, and to get you interested in security further by showing you how to craft your first exploits, because security is indeed a really fun field. So you will see that it's quite enjoyable to try to attack your own contracts or your own examples and trying to crack the correct answer to each of the mental challenges that you can impose yourself. So I have already shared yesterday, I think, this GitHub repo. There you will find first, of course, the vulnerable examples of each type of reentrancy that we will be revisiting during the workshop. But in addition, you will find also templates for attacker contracts. So although we won't be able to wait for you to actually craft the data killer contracts during the event, because that could take a lot of time. You can, of course, take these templates and after the event, try to actually create your own exploits based on what you have learned and what you can see on that repo. So you don't need actually actual Foundry knowledge for this, because I have already provided the test cases and so on. So although this has been prepared using Foundry, it doesn't matter. So you will be able to just run the test command and check if your exploitation is successful or not. So first things first, let's review the basics of reentrancy. You probably already know all of this, so I will be a little bit quicker in this section. However, it's still interesting to go over it again. So as you probably know, we have a reentrancy back in Solidity when contract A, that will be the victim, calls contract B, that will be the attacker. Sorry, contract A, that will be the attacker, calls contract B, that will be the victim. Then contract B calls contract A again, but before contract A has updated relevant state variables, and that's the most important part. So now the control flow is given back to contract A, that is our attacker, so that attacker can call again this same function, so it can re-enter the function that haven't updated its state variables yet. So we'll be having a different kind of like a type of unexpected situation. So an attacker could leverage this to, for example, the most common impact I would say is to be able to perform an action multiple times, as that has never been done before. So for example, you will be able to withdraw more than you own in the case of a vault, or you will be able to claim the same price several times. And it will depend a lot on each case, but this is the overall basic idea. So these are just two basic examples, as you will have seen a million times, like from the book one, but just to review the overall flow. As you know, the
just wanted to check. Sorry, JC.
Yes.
Is your screen? Have you changed your screen at all? Just want to make sure that it actually is operating, because it's been frozen on the same screen.
What is the slide that you are seeing right now?
I think I'm not the only one, but we're seeing, I think it's 01.
VS Code.
VS Code? No, you should not be seeing VS Code at all.
Yeah, we've been looking at VS Code the whole time.
Yeah, not awesome. So you are not seeing the slides right now?
No, sorry.
VS Code.
So, and are you able to see the browser?
It's just the Explorer. We can see the Explorer.
Yes.
Yeah.
But so you see the Explorer, and when I hit present, you don't see the slides in widescreen.
No, sorry.
That's catastrophic.
We were listening intently though. Is there a way? Should we try and
let me try to share the screen again, just in case.
Yeah. Let's go for that.
Yes, I think I found you share. Yes. Are you able to see the slides now?
Yes.
Okay. So, but am I able to change to VS Code? So do you see VS Code now?
We can't see any VS Code right now.
Okay, awesome. So the problem is that I am just sharing one window and not the whole screen. Okay. Yeah, the incorrect option was chosen. So now you are seeing the slides, and now you see VS Code, right?
Perfect. That's it.
Okay, awesome. Very sorry for that.
Cool. At least I didn't get half the presentation, and then we were like,
yeah.
Fine.
I mean, it was just like the overall informative stuff until there. So the interesting details started now. Thank you for catching that. So yeah, as you can see here, we have two basic contracts. The one in the left is the victim. It's just a plain bold that allows us to deposit and then withdraw. And the withdraw function doesn't follow the check effects interaction pattern. So it will perform the interactions before the balance update. And on the right side, we have our attacker contracts that use resize as a mean to loop and re-enter again into the victim contract. The fallback function, as you know, could also be used, but in this example, we'll use resize mainly. So we'll just start the exploit. First, we will do an initial deposit, then call withdraw for the first time. And when we call withdraw, the thing is that at line 10, it will give the attacker the control back by calling its resize function. So at this point, the attacker will be able to re-enter the withdraw function. But as you can see, the balance update, in this case, the balance equals 0, has not been executed, but we are entering withdraw again. So the balance that we will be withdrawing in the second round will be the same as in the first round. And we can do this again and again. It will call withdraw, it will go resize, it will go withdraw, and we will be able to loop into that until we are able to drain all the funds on the contract. So although I have crossed out the balance update, it's not that it never gets updated, but it's done at the end of the whole looping of executions that we have shown. So let's take this example where we have re-entered 2 times. So the execution flow will look like this. First, the victim will check the balance of the attacker and then transfer the attacker. The attacker resize function will be executed, where the attacker will re-enter again, withdraw. The victim will again transfer the attacker, resize will be executed, and withdraw, re-enter again. But this last time, the whatever stock conditions that we add to our attacker contract will not continue the loop, the exploitation. So the thing that happens here is that the remaining lines, the state updates that we have not done before, will all be done now. So first, the latest one will be executed, then the one before that, and finally the first execution of withdrawal will update its balance. So this is the main idea of how a reentrancy works, that you are not only looping around, but you are actually leaving some execution pending. So some well-known recommendations. We'll work this list during the whole presentation to improve the coverage of our recommendations, but the most basic ones are, of course, to add a mutex like non-reentrant, the non-reentrant modifier, to follow the check effects interaction pattern. This is the most important one, and one that I have heard in the past that you should not take as an acceptable recommendation is to just use send and transfer instead of call to transfer ether. So why not? Because the gas cap that these 2 functions have kills composability. The ability for the resize or fallback function to execute upon an ether transfer is not a bug. It's actually a feature that is used to create all these money Legos that we always talk about. Then the second problem is that gas cost of operations may change in the future. So although at the moment it's not possible to perform convoluted exploitations due to the gas limit that these 2 functions impose, that may change in the future. And this is not something that I myself came up with, but it's the reason why these 2 functions are going to be deprecated in Solidity 0.9 in the future. So here we have Anakin and Padme that will help us to rethink these potentially weird scenarios during the whole presentation. So you will be seeing them a lot. So let's start. We have seen that ether transfers can give away the control of the execution flow, right? Okay, then we have nothing to worry about if we are transferring tokens, because tokens do not trigger the receive or fallback functions, right? What do you think? Should we be worried when transferring or moving tokens around? This is the easiest one. So in general, the idea is that yes, because although transferring token do not trigger these two functions, there are several token standards that have callbacks. So for example, when the ERC71 SafeMint function is called, it not just means an NFT in this case, but it will perform a callback to the recipient. So the problem will be similar to the case of transferring Ether and triggering receive or fallback. This is not just a thing that affects the ERC71, but it also affects several others, for example, the ERC777 and 1155 and others. So usually always be careful about a little bit of sometimes unknown or unexpected callbacks happening in some of the standard token functions. So we will see finally our first example here. This vulnerable example is a basic ERC71 implementation that just exposes one function. Any address is only able or should only able to mint one NFT, and this is controlled by hash minted. And there is a maximum of 10 tokens that can be minted with this contract. So the expose function is mint. This mint function uses safe mint underneath, which causes a callback, as we just mentioned. And this function doesn't follow the check effects interaction pattern. So it updates has minted at the end, causing a potential vector of reentrancy.
JC, so, just a quick question for Shivam. You mentioned in the last slide about something being deprecated in V0.90.
Yes.
That seemed like I missed it. Yeah, what was that certain thing?
Yeah, both the dot send and dot transfer functions to move Ether around, those two are going to be deprecated in the future. So at the moment they are still like valid options, but the intention is to deprecate those in the future.
Perfect. Thanks for that.
No problem. So let's see our first example. Yeah. Are you able to see the VS Code now?
We're
okay,
very
awesome. Attacker now talking callback. So this is our first example. Is very basic. It's just one of the NST ones that, as I mentioned, it exposes mint. It first checks that the user has not minted any other NFT before, that the supply is below 10, and then the safe mint is executed. As we have mentioned, this will cause a callback, so this function is not following the check effects interaction because the flag that marks that the user has already minted, and a token in this case is done at the end after the callback. So our attacker will be able to gain control of the execution flow here. So how does our exploit look like? So the first thing what we have to do is to actually implement a callback receiver in the attacker contract, of course. As we don't have receive all fallback, we have to implement one of the receivers that are defined by the ERC71 standard. Then we will call mint a first time, and our receiver will call mint again. So this is very similar to the basic reentrancy that we just showed. However, instead of looping between the receive and the affected function, it will loop between the on ERC71 receive function and the affected one, in this case, mint. So let's look into that. As I mentioned, very easy, very short. We just have to call mint the first time to initiate the exploit, and inside our receiver we will call mint again. This try catch is just so the stop condition is that the victim contract is returning an error that all FTs has been minted. So let's run this example first. You have the Foundry commands in the README of the repository. So you have to look into the README. You want to execute those exploits. So as we can see, these are just some pretty printing of the states before and after. So we are able to see what happened during this exploitation. So the initial situation is that the victim supply is 0 because no NFT has been minted yet, and the attacker's balance is 0 because as no NFT has been minted yet, of course, the attacker doesn't have any NFT. So after our reentrancy exploitation on this, as we have shown before, the result is that all NFTs has been minted, and all of those has been given to the attacker. So instead of just one, as the specifications dictate, our attacker has been able to get all the 10 NFTs in this case. Okay, so has it been enough to just be wary of Ether transfers? No, as we have seen. So let's review our well-known recommendations. Of course, we can always use non-reentrant, but the important thing here is that we should follow the check-specific interaction pattern in every external call, not just in Ether transfers. And in particular, we should be aware of these unsuspected callbacks in some token standards. Not just the NFT one, but a bunch of others, as we've shown in previous slides. So here we have Anakin again. As all of you probably know, the mutex will revert, the non-reentrant modifier will revert if the protected function is to be re-entered. So if we just guard any function with external interactions, we will be safe, right? Because I mean, those wouldn't be able to, wouldn't be re-entered, so the exploitation will not be possible. So as you probably already know, because we are here sitting looking at this presentation, we have some additional things to worry about. So let's present cross-function reentrancy. This is also more or less basic. So again, you probably already have seen this before. The main idea is what could happen when different functions use the same state variable without one of them following one of the functions following the check-effects interaction pattern. So we will take our basic reentrancy example and add a little tweak for this case. So we have our withdraw function that doesn't follow the check-effects interaction pattern. So our developers has decided to just stamp a non-reentrant modifier on it to solve this situation. But we have a new feature in this new feature in this contract that is a transfer tool function that allows us to move funds around in the internal accounting of the contract. So we don't have to withdraw the funds and send those to our friend, so our friend can deposit back. We can just use this transfer function within the contract, right? So let's look into this. It's quite easy. So cross function, yeah. So as mentioned, our basic deposits, our vulnerable withdrawal, because as we see, we are sending back the Ether before updating balance, but this function is protected by the non-reentrant modifier. And here we have our transfer tool function that, as I mentioned, is just move the accounting of Ether in this case from the sender to the recipient. These functions do not perform any external interactions and so on. So we have not considered this to be dangerous, and we have not added non-reentrant here because, well, as it doesn't perform external interaction, why we should care about this. So how will we exploit this scenario? It's similar to the one before, but until some point. So we for sure perform the initial deposit and call withdraw to trigger the exploit. And from our reside function, if we call withdraw again, will receive an error because of the non-reentrant modifier. So that's the part that differentiates this case from the previous one, that we will receive an error if we try to call withdraw again from inside receive. So what we'll do is to call transfer to. So we will be able to transfer all our funds, the funds accounted by the contract, to another attacker controlled address. So what we have achieved with this just basic linear execution is to be able to double spend the same amount, because we have been able to first withdraw our funds and then move those funds to another account controlled by, of course, us, the attacker. But we can upgrade this this exploit to be able to drain all the funds by using two contracts that both of them perform this same pattern. So one contract will withdraw and transfer the funds to the other. So then the other will withdraw and transfer the fund back to the first one. So they will be like playing a little bit of a ping pong game, like performing double spend after double spend until all of those has drained the funds. So let's look at how this will look. Yes. Okay. So we have added a little bit of a more uncommon additional function here, that is the set psychic. This function is just so both our attackers are able to see each other, so they are able to call the other one after performing the first double spend and so on. Our exploit function follows the steps that we have mentioned. So first we do the initial deposit, then call withdraw. This withdraw will trigger the receive function that performs the transfer to, as we have mentioned. And after this has been executed, if there are still balance left on our victim, we will call exploit on the other attacking contract. So the other attacking contract will do the same. We'll deposit, withdraw, and trigger double spend, and then calling again to the first contract. So if we do this until there are no more funds left into the victim, this is number 2 here, right? Okay. Into the victim contract, through the usage of these two attacker contracts, we will be able to turn this double spend into actual a drain of the whole balance. So as we can see, the initial balance of the victim was 10 Ether in this case, and the attacker's balance is 2. This is because we have two attacker contracts that these two is just like the addition of the balance of the two contracts. So in this case, 1 + 1. And after the exploit, we have fully drained the victim's balance and the attacker's balance, or the addition of the balance of the two, because it will be split half to each attacker, because they have been like taking turns during the exploitation. They will hold each of them half of this pot, effectively again fully draining the victim instead of just performing one double spend. So is this one clear? Because we are going to start hopping into the more interesting stuff. So okay, I will take this as ready to go. So let's review our recommendations one more time. Is it enough to just set a mutex in the function that have external interactions? The answer is, of course, is no, as we have seen. So let's review our recommendations. We will not be adding anything to the follow checks effects interaction 1 yet, but we will see that we know now that adding a mutex to only to those functions that perform external interaction is not enough. We have to add the mutex to every public or external interaction. So we are not able to exploit this scenario by using a different function than the one affected by the reentrancy or the lack of check effects interaction pattern. Another option will be to use a global non-reentrant pattern. That is something that we'll mention at the end. But the idea is very similar, that it's not just one function that is protected, but all of the functions in the contract. So now we can look again at this slide that we have seen before. Now that we know about cross function, this example was directly exploitable because the state update, in this case line 12, it just assigns a new value, so there's no issue there. However, if this line could raise an exception, for example, by checking a potential underflow upon subtraction, the whole transaction will revert, and this exploitation could be unsuccessful. This was the example that was shared on Twitter before, the challenge of what's the difference if their state update subtract the withdrawn amount instead of just assigning it to 0. So let's briefly look at the main idea of how we can exploit the situation, as indeed it's closer to a cross function or even a cross contract exploitation. So we'll try to first execute. Yeah, we have an example that we'll just try to exploit this case as, no, this is the one. This is the one. It will just try to exploit it as we used to exploit these kinds of scenarios. So we'll actually see the error that is being raised here, because Foundry has very nice traces. So it's awesome to do a little bit of debugging in case our exploits or our tests are failing, because we can see all the calls and all the reasons why something has failed or not. So we will start to loop around receive and withdraw, with the receive and withdraw, etc., until we reach the stop condition here. So we see that this first withdraw sum finalize its execution correctly, because we'll be setting our balance to 0, because we will be just subtracting the whole balance. However, the next iteration will throw an arithmetic overflow, because as our balance is zero, before that, if we try again to subtract 1 ether, of course, it will trigger an exception and it will make our whole call fail. So how can we exploit this? Subtracting the balance, as we have seen, will end up reverting the transaction. Then this shouldn't be exploitable, right? Sadly, it is exploitable. However, I have chosen just a random example, but what I want here is that you get the idea, because this is the scenario that I will show you is just a very specific one, but the overall idea of how this will be exploited is shared in every case of this, like subtracting reentrancies, to call it something. So our goal in this kind of scenarios will be to benefit from a situation where, during a short amount of time, that is like in the middle of a transaction, we are able to reduce the balance of the victim to 0 or to a minimum, and we are able to hold all the funds. So if we don't want the transaction to revert, we should return all these funds. So those are not the funds that we will be keeping. So that's not our price for exploiting this, but just a mean for the final exploitation. So we can leverage a situation where we have changed unexpectedly the whole balance of the victim, or we can perform some kind of a free fee flash loan, as we will be holding all the funds temporarily, but we are not paying a fee. We'll look at this example will take advantage of the third case, of the case where the victim's balance is reduced to 0. So the example that I am showing you right now, it looks similar to one of these tokenized vaults, the ERC 4626 standard. We'll have common deposit functions that, of course, receive ETH from the users, and then our withdraw function that doesn't follow the check effects interaction pattern, but instead of withdrawing everything, it's actually performing a subtraction. So if you try to perform the exploit as we have done before, we will receive these errors that we have seen in this case, right? So the additional functionality that this contract has to allow us to leverage the situation are stake and unstake functions. So when a user stakes part of all of their deposit, the contract will create some shares, which initially they will be like 1-to-1, 1 share, 1 ETH. However, the price will change if the underlying balance of the contract changes. So for example, if this contract receives some donations or have some kind of reward collection mechanism, that is something more or less usual, the price of our shares will grow. So instead of just redeeming 1-to-1, it will redeem, for example, 1-to-1.1 or something like that, right? So we will not look into the code of this example. The code is there if you want to actually try it, but as this is a very specific case, I don't think it's interesting spending time looking into how the tokenized balls are implemented. But we will look into the exploitation steps because that's the interesting part here. So again, we will perform the initial deposit, and then we have what I have called phase 1. Phase 1 is where we will manipulate the share prices. That is just performing a basic reentrancy exploitation as the ones that we have seen before. But instead of just ending the exploitation right after, because we will receive an exception here, we'll continue with just leaving one way is because the formula to calculate the shares, it's better if we leave the contract to a minimum instead of 0, but that's not very important right now. So we'll get into a phase 2. That's where we will leverage the fact that the contract's balance has been reduced. So in this case, we will deposit and stake just 1 ETH. And what will happen is that as the formula followed by the tokenized balls calculating the shares is the one that we are seeing in the screen, we will receive a much bigger piece of shares if the balance is reduced to a minimum, because as you have seen, it's in the denominator of the division. So it's not the same if we are like dividing by the amount that we are inputting and what has been there before, rather than just between one way. Because for example, let's imagine that the contract already have like 30 Ether staked with 30 shares minted, and we are staking 1 ETH. So in this case, 30 multiplied by 1 divided by just one way. Remember that the numerator is in ETH and the denominator in way. This will give us a very big number. So this phase 2 is what happens while we are holding like the looped exploitation of phase 1. So in order for this to not fail, we have to repay the manipulation done on phase 1. So we'll just deposit back all the funds that we have withdrawn during phase 1, and our exploitation will be finished because we will be able to redeem all of those shares that we have, the disproportionate amount of shares that we have minted on phase 2 at the end. So let's look at the execution now, because I have added some logs here, so we are able to see how this is 2B. How the price of these shares are changed after the manipulation. So this scenario will show us that 3 users have previously staked their ETH in the contract. So Alice has gotten 10 shares. This is not 10 shares, but 10 multiplied by 10 power to 18. So 1 for each way. Bob the same, got 10 shares, Charles 10, and so on. So the final balance of the contract will be 40 because it has already been used, and our attacker will hold just 1 ETH in their wallet. So as we have seen, the price of the ETH of the shares here is 1-to-1, but after performing the price manipulation that we showed on phase 1, if we try to deposit and mint shares for us, we'll receive a very different price. So in this case, our attackers has taken just 1 ETH and receive this amount of shares. And this is not because I forgot to divide it by 10 powered to the 18, but this is because this is multiplied. Also, this has to be multiplied by 10 powered to 18. So indeed, this number is very, very, very big. So now the attacker holds the majority of the shares in the vault. And after paying back our phase 1 exploitation, the shares will go back to be at 1-to-1 price. So we have a bazillion shares that are worth a bigger proportion of the ETH. So when we redeem all of these shares, we will get most of the contract balance. So the victims balance will be reduced to a minimum, just 41 way, because we can't reduce it to 0 because of this example. And our attacker will have to redeem the majority of the shares and the majority of the ETH just by staking and 1 Ether. So, this is a little bit more convoluted, I know, but it's a very interesting example because it looks very, 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 very similar to the basic one. But as you can see, the exploitation is not similar at all because it requires like further steps. Again, all of this code, the code from the victim examples and the templates, it's on GitHub. So the idea is that you get all of this step in your mind and then you try yourself, because that's how you will actually learn and enjoy, like trying to craft your exploits and so on. So here we have Anakin and Padme again. After looking into cross-function reentrancy, we have learned that any public or external function of the contract could be re-entered, right? Not the function, but the contract could be re-entered from any entry point. Therefore, if we make every function of the contract non-reentrant, that will be enough, right? Because then the attacker will not be able to re-enter any of the external functions, and they will not be able to exploit our contract. Again, I'm sorry, but this is not the case. So let's get into probably the one that will be newer for all of you, that is cross-contract reentrancy. It follows a similar idea to cross-function. However, the thing is that instead of using 2 different functions to perform the exploitation, it will choose 2 different contracts. Not 2 attacker contracts, but 2 different victim contracts. So our example here is very similar in idea to the one seen before, the one of the tokenized vault. However, the thing here is, the thing that differentiates this to the previous one is that instead of just having an internal accounting for the shares, we are actually having an ERC20 to actually represent those shares. So this has been simplified to be always a 1-to-1 value for the sake of simplicity in this example. So anyone can deposit 1 ETH and they will receive 1 synthetic ETH. It's not the official synthetic ETH, of course, but just one name, for example. And they can unstake this synthetic ETH. It should, sorry, just a mistake. It should be, they will be able to withdraw the ETH that their synthetic ETH is worth, but this withdraw function will be the one that is not following the check effects interaction pattern. However, this function will be marked non-reentrant, and all other functions will be marked non-reentrant, so we won't be able to perform the same exploitation as we did before. And on the other hand, we have the token contract that is just a very common burnable and mintable ERC20, but we have an additional function called burn all, that just burns the whole balance of a given user. So let's look into the code. This is the attacker and this is the victim. Okay. So as I mentioned, the victim is quite easy. It allows us to deposit, just minting one synthetic or one token for each ETH that we have deposited. And during the withdraw or unstake function, we'll just burn our whole balance at the end, and in the middle, for not following checks effects interactions, we will receive the transfer of what all of those tokens were worth. So this is very basic, but as I mentioned, both of them are protected by the non-reentrant modifier. So we won't be able to perform a cross-function exploitation here, because there is nothing that there are not other functions that we can successfully cross to perform exploitation. Let's look also into the token contract. It's very easy. As I mentioned, it's just an ERC20 that is both mintable and burnable, and the functions that differentiates the most is this burnal one that has been added just for simplicity of operation, because it just calculates or queries the whole balance of one user and will burn the whole stake at once. So okay, so those are our victim contracts. And how can we exploit this? This exploitation will look again very similar to some of the ones we have seen before, but with the tweak that we are not actually doing just we are not just calling functions from the first contract, the vault, but we are calling functions from both contracts, the vault and the token. So we will perform our initial deposit, we will call unstake, and from our receive function, we will call unstake again. We actually can't do this because of the non-reentrant modifier, as we have seen before when dealing with non-reentrant modifier. So what we'll do here is to call to the contracts transfer function. As we saw in the cross function example, we were calling this new feature of transferring the funds within the contract. In this case, it's very similar, but it's an external one. So we will call transfer on the token contract. And again, we will be able to achieve this double spend situation where we are able to withdraw our stake and also transfer our stake to another attacker controlled account. Again, this case can be upgraded using the same approach with two different attacker contracts ping-ponging between each other, performing one double spend after one double spend until they drain the whole contract. I'm not going to run this proof of concept because it looks very similar to the one before, but let's look briefly into the attacker's contract. So this is the attacker. As in the cross function case, we have the set psychic function here, so they are able to see each other. However, inside of the resulting function, we are calling a function from the token contract instead of the target that will be the vault. That's why this is called cross contract, because we are actually using two victim contracts to achieve our exploitation. So will making every function non-reentrant be enough? Not the case again. We have to consider that other smart contracts could be used as part of this exploitation if our contract interacts with them. So let's review our well-known recommendations list. Adding non-reentrant has not been enough in this case. We have added non-reentrant to every function in our contract, but still the attacker was able to profit from this. So we have to go again into the checks effect interaction list and highlight that we should follow this pattern in every external call. Doesn't matter if we have non-reentrant, we have to actually follow this if we want to fully avoid reentrancy situations, reentrancy bugs. So we are looking towards the end of the presentation now. So we have already found here, following the checks if interaction should be our primary line of defense. So if we are following this pattern, that is taking the interactions to the latest bit of our functions, plus using non-reentrant, because it's always a double check there, we should be safe, right? Because that's what the recommendations usually recommend, right? To use these both patterns and these both mechanisms, and we should be safe, right? Again, the reentrancy ways are complicated sometimes, so there is still some cases where this is not enough. So I want to present you read-only reentrancy. It's not so well known, however, like probably if there are something more acquaintance to security here, you have been already at least hear about read-only reentrancy. Indeed, it's just a subtype of cross-contract reentrancy. It's very similar, so let's look at the differences. So contract A could issue some kind of callback in the middle of the execution at a point where not everything, that is, for example, balances or state variable, has been updated yet. And the other contract, the victim contract, will read information from the first contract A. That is what is called read-only reentrancy. So the problem here is that the traditional implementation of the non-reentrant modifier do not support view and pure functions. So we actually can protect with the non-reentrant modifier every function in our contract, because the view functions will not support non-reentrant. So as the view function will not be protected, the other contract will be able to call again into this view function. And during this callback, the point is that the information retrieved by this view function will not be showing the complete information, because it will be in a middle state. So this description has been a bit messy, but we have some drawings, arrows, and boxes here that will clarify everything for sure. So we have here our attacker contract, our victim contract A, and our victim contract B. So when our attacker contract calls F1, F1 will perform a callback to the attacker because of the of something that we'll see afterwards. And during this callback, the function the state update will not be finished yet. Therefore, the view F2 will be reporting an incomplete information from contract A, something that doesn't reflect the actual finalized state. So now during this time, the attacker will call contract B, and the thing is that contract B uses the information retrieved by F2, the view function of contract A. So when contract B tries to retrieve this information, they will receive incorrect data that our attacker could leverage to get some kind of benefit from this. So the contract A has been re-entered indeed, but re-entered as a view function. That is why this is called read only, because we can re-enter the contract, but just in a read state. So I have put together an example. It's a little bit convoluted because these read-only cases are not so common. They are like more usually seen in liquidity pools. So we have two contracts, a liquidity pool contract. In this case, we will be using ETH and synthetic ETH. All the functions will be marked as non-reentrant, and the interesting thing is that the remove liquidity performs the following actions at the end of the function. It will first burn some LP tokens, then transfer the first asset, and then transfer the second asset. So the thing here is that this read-only reentrancy will only affect liquidity pools that where some of those assets perform a callback. I have chosen ETH and synthetic ETH, that is a random ERC20 token for simplicity. And you could say, well, then you can just move the transfer of ETH to the latest stage and you won't receive a callback in the middle. Yes, that's correct. However, what will happen if instead of just ETH and ERC20, we have, for example, two tokens that perform callbacks, like, for example, two ERC77 tokens? Then you won't be able to perform like an ordering that avoids callbacks at all, because both tokens will be performing a callback. So when this first asset X is transferred, its callback will be exposing what we have said to be an incomplete state, because as token Y could not have been transferred yet, the balance of token X will have already been reduced to whatever we are, the amount of liquidity that we are removing, but not the one of token Y. So we are exposing a situation where, for example, the price, the spot price of return by the liquidity pool will be manipulated, because the two assets will not be atomically removed from the pool at the same time. They will be done first X and then Y, and in the middle, the price will not be the real one. So the other contract could be just a random lending contract for these same assets that lends, in this case, synthetic ETH, over collateralized and so on. And the thing here is that it will queries the spot price of this liquidity pool to calculate the collateral. So if we look back to our boxes, contract A will be the liquidity pool and contract B, the lending contract. So if we have not removed the two, as it won't be possible to remove both assets at the same time after removal of the first one, for example, let's say asset X, the attacker will receive the callback. And when the contract B tries to calculate the collateral that it's required to perform this borrowing, it won't be seeing the actual price of these two assets in the liquidity pool, but some misguided information, because there are still some asset pending to be transferred out. Yeah, this is a little bit, as I mentioned, the example is a little bit convoluted, but just to show you the basic structure, add liquidity, remove liquidity, and at the end we have the three actions that I have mentioned. We first burn the liquidity pool token, then transfer the ETH, and then transfer the synthetic ETH. So what should we do to exploit this scenario? We first will add liquidity to the pool, of course, and then remove liquidity to the pool, because the remove liquidity is the function that actually triggers this read-only exploitation that we just showed. So from the receive function of the attacker, instead of calling again the liquidity pool, we will just borrow synthetic ETH, because that will be when we receive this callback, when the receive function is being executed, will be the point where the price will not be the real one and will be different, and will allow us to get a better deal when borrowing synthetic Ether. So the result of this particular example could be that we'll get under collateralized borrowing of synthetic ETH. This scenario that I have prepared for the exploitation, it's a little bit extreme to be able to showcase the benefits. In general, in real life, the benefits has not been so widely big as the guys that we'll see here now, but it is easier for you to get the idea with this. So our attacker contract, as I mentioned, will first add liquidity, then remove the liquidity. This is just some printing, so we are able to see the price during the whole process when I execute the exploitation now. So remove liquidity, And from within the receive function, we will perform this borrowing of synthetic ETH, paying whatever collateral is required to perform this action. That is, here there are some percentage defined by the borrower, that lending, sorry, by the lending contracts. So as soon as we respect those limits, we are able to borrow that ETH. So let's execute this last example. I added some printing of prices in the middle, so we are able to actually see the different stages of the exploitation, because if not, it will look just weird. So there is some initial deposit that is very small, so the benefit looks bigger in comparison. So our attacker will first add liquidity. After adding liquidity, the price in this case could be 1-to-1. So one synthetic ether have a price of 1 ETH. Then we actually start of the part where we will call the exploitation. So we have added liquidity. We are removing liquidity now. So we just receive a callback. So the receive function is being executed. So here we are going to call borrow ETH, but the price that we are calling borrow ETH is not 1-to-1 anymore, but 1 to 0.3 ETH. So we are getting a much better deal, being able to borrow synthetic ETH at a half the price of ETH instead of over collateralized. It would be under collateralized. And when the remove liquidity function finishes, the price goes back to normal. However, we have been able to take a loan that has been under collateralized instead of over collateralized. So the balance of our attacker at the end could be almost half Ether bigger than it was at the beginning. Okay. So there are some cases where even following the check effect interactions and adding multi-sex will not solve all of our issues. That is because the non-re-entrant modifier, the common implementation, is not suitable for view functions. So in order to solve or to protect us against this kind of read-only re-entrancy issues, we should we could add some tweaks to the non-re-entrancy. One will be to make the log publicly accessible. So, for example, contracts that interact with this one will be able to see if the contract has already been entered or not. And other option is that within the view functions, we just check the flag that has been set by the mutex, not using an oriental, but just directly check the flag. So the last one will be cross-chain. We won't get much into this one because it's not very common, but it's a very interesting one to be aware of. You can check this article here that shows a basic example of this scenario, but in a cross-chain environment. So if you are interested in this kind of stuff, I will recommend you to read it. So we have finished the review of all of the re-entrancy types that I wanted to show to you today. So let's look at our summary of fixes, because we have been creating a bigger list of recommendations as we have seen each different type of re-entrancy. So the first ones, of course, follow the check effects interaction pattern, but not just in the cases where ETHs move around, but in every external interaction. That includes tokens, as there are unsuspected callbacks sometimes, and that also includes contracts that are in the protocol or trusted, because they can be used as part of the exploitation. Yes. Another issue with protocols with several contracts is that the control flow can be very complex and may end up giving the control back to the attacker at a point that we are not aware. So we should also consider trusted contracts, not fully trusted in this case. Then the other one is to add a mutex like non-reentrancy modifier. That's okay, but we should add those one to every public and external function. We should also consider making the log publicly accessible, or checking the log in the view functions too, to avoid read-only reentrancy. But as we have seen, this may not be enough in some scenario. Yeah, as I mentioned, the global non-reentrancy pattern is a little bit of a niche implementation that it is not still very so widely used, that make use of an external contract that is the one that holds the flag. But maybe in the future that becomes the trend, not now at least. So that has been all for today. I know that this has been intense for just 1 hour, but I had too much material to show to you guys. So sorry for the extra time.
Not a two, no. We started at like 5:05, so that was pretty much an hour. That was brilliant. I mean, that was an awesome workshop, JC. It's pretty crazy to think, like, for such a common attack, that reentrancy has so many misconceptions and kind of blind spots.
It has like so many extra phases that to look into.
Yeah, it's insane. And yeah, you clearly put a lot of kind of time and effort into that, and you explain things really well in great depth. So yeah, truly interesting stuff. And yeah, I think it's a massive thank you for sharing all your knowledge with us.
No problem at all.
If you'd like to. Yeah, big round of applause. Thank you so much, JC. Incredible.
Yeah.
Do we have any questions at all from the audience?
Do you have any mutex recommendations? Well, wait. Okay, do you have any mutex recommendations? I mean, like non-reentrancy contract from OpenSepli, and also where can we get the recording and the PowerPoint? The recording and the PowerPoint will be, I suppose, given to you by the Calyptus team. About recommendations, the thing is that it's not that the OpenSepli implementation is not good. It is very good, and it has been reviewed 1 million times, so it should be trusted. The thing is that those implementations do not cover every case if you use them just like you have been using them until now. So just stamping non-reentrant. Stamping non-reentrant is not enough, but the implementation is correct. The thing is that you should check that flag inside of your view functions, for example, to stop the read-only exploitation scenarios.
Good stuff. Any more?
I recommend all of you to clone the repo and try it yourself, because one thing is that someone speaks like for 1 hour about this topic and so on, and all, it may look cool, but you will learn a lot more if you actually try it yourself. You will have a much clearer visualization of what is happening. I've seen that someone asks, for example, about a flow of the cross-function reentrancy. Please try to exploit the cross-function reentrancy, activating Foundry traces, the ones that I have shown before, where you see all the calls during the execution. That's a very easy way to look into what's actually happening during the exploitation. Can you please guide me on the go? Okay. And I want to ask if you can provide with some roadmap that I can follow about security and auditing. You have a bazillion roadmaps out there. Some of them are very good. So although I can't think of a specific recommendation from the top of my head, for sure you will be able to find some that are very complete. So yeah, there are a lot. Will there be any workshops in the future? I don't know. And if we have some questions regarding the workshop, can we ask on LinkedIn? So as Calyptus was the organization that invited me here, I will prioritize the question asked through the Calyptus Slack. I will try to ask to also reply to questions through other social media, for example, LinkedIn that you mentioned. But that will happen when I get enough time to do that. But the ones prioritized will be the ones in the Calyptus Slack as a thank you for this opportunity.
I appreciate that. Cheers, Jesse, and we'd love to have you on again. You know, there's obviously so much to cover in auditing and all these different topics. I didn't know Reentrancy even went that deep. So, no, it's an amazing presentation, and thanks so much. Anyone who hasn't signed up to Calyptus already, I just put the registration link in the chat. Sign up. We have events every week. I hope to get JC back as well for another workshop, jobs, solidity lessons, everything. So
Sure.
and it's all free.
For sure.
So yeah, thanks again, JC.
Thank you, Primal. Thank you very much for inviting me, and thank you everyone for staying with us for one whole hour.
Not at all.
Thank you, JC.
Cheers, guys. Thanks
See
for
you
coming.
all in the community. Bye-bye.